The page, shall I do a little introduction before Dr. Georgiev lecture, or because I see the screen?
Well, yes, I think Dr. Georgiev has just set up his screen, but yes, I think that we should probably follow the same schedule as the last meeting, where you say, you make some comments, perhaps, it's up to you as to when during the meeting you would like to address some of the points on physics that were raised after the last meeting.
It will be because the physics is the physics of what Dr. Georgiev will present. I think it's best to know it in advance to avoid ambiguity, and but that's up to you. For me, it's the same. Okay.
Okay. Well, of course, since Dr. Georgiev is the speaker, I think he also should state a preference in terms of how he'd like to manage the presentation.
Yes. So I have read very carefully all questions, and I think that such lectures, starting with the ISO field and ISO numbers, ISO point, Iso-Analytic geometry, there is a big need so that to be introduced the other things with ISO tangent line, ISO surface, and so on.
Yes, I agree with that in principle, that most of the questions were not so, well, my interpretation was that they're not so much about physics, but rather interpretation of the mathematics at this point, so physics, at least temporarily, is sort of a kind of illustration of this particular kind of mathematics. So where we're at least temporarily placing the mathematics first, but maybe that's maybe just my own personal view.
The problem is Dr. Subject, as well as others, they still have just of course fully legitimate reservation on what is the isotopic element, what is the iso unit. And that's what I want to elaborate. Otherwise, their reservation on the very, very fundamental notion of isotopic element and iso unit that will carry over throughout the entire lecture of Dr. Georgiev.
Yes, personally, I also feel that I'm really only at a very elementary level, and I still have a great deal of difficulty with even a geometric picture of what this iso unit means, and even what the meaning of the actual way, the correct way to interpret isofunction. It seems to me still very unclear. I think I understand the motivation, from the point of view of why one wants to look for alternatives in physics, but I still have trouble with the mathematics personally.
Because the variety is the variety, is the variety of realization. In other words, the notion of tangent, unless we specify what the iso unit is, it becomes very, very undefined.
Well, and it's all, for me, in terms of interpretation, it is tangled up with this notion of what you have frequently referred to as locality. So being a function being defined at a point versus something else, which the something else for me is still very unclear. But since when I think of function, I think of a function as being defined at a point almost by definition. So the transition to isofunction is a difficult one for me, because I don't see in at least the definition so far where non-locality comes from.
Well, because the risk that I'm not sure what I'm about to say, but the risk is, that the notion of function is totally non-existent, cannot even be defined in isomathematics. Because it's a function of an isocoordinate. An isocoordinate, the meaning here is where the problem originates. Because what is the meaning of an isocoordinate? And
Yeah,
unless
I think, but let's not get into the specific details yet, or at least let's try to.
let me finish the sentence, Dr. Page, please.
Okay.
The difficulties, we don't communicate at all. So let me try to restart and then I'll be silent. Do you see the notion of isofunction? You ask me what is you have a very precise mathematical definition. And then you want to understand what an isofunction is. That's where the problem are. Because in my opinion, it cannot be understood in general since there is an infinite variety of possible iso units. The iso unit can be a constant. And so we have one notion of isofunction. It can be a local variable. It can be an integral. It can be surfaces and so on. So the problem originates when you try to understand an isocoordinate, and they cannot. You see, when Dr. Cruz asked Dr. Georgiev the other, what is an isonumber? Dr. Georgiev gave him immediately the correct the answer. An isonumber is a number divided by the isotopic element, exactly what I introduced in my first lecture, is a number multiplied by the iso unit, which iso unit is the inverse. So there's the precise mathematical definition. At the mathematical level, period, that's the definition, that's a ring, that's verify the action and so on. All problem originates in you try to interpret what is the meaning, and that's where all the problem, but in my opinion, again, this is an impossible, there cannot be any answer, there will never be, because you cannot give one single meaning to an infinite variety of possible realities, so you have to specify. And one final point that will, I wanted to clarify before the Dr. Georgiev lecture, this was Dr. Sapsik justly asked the question, what is an isotangent? But again, you see, the question makes me very, very uneasy, because it cannot be answered unless you specify the iso unit. If your iso unit is a number, then it's a very conventional notion. If the iso unit is a function, then you have a new geometrical notion in which the tangent changes continuously in the manifold in which you are. If it is an integral or it is a void. So the answer that you ask can only be specified, can only be answered, as far as I know, with a selection of one among the infinite variety of the iso unit. It's like asking, what is the force in Newton's equation? That was my introductory comment. You cannot define, you can only define as a dimension, as the dimension of a force. Then you have an infinite variety of force. And you cannot conceptualize, because you have to be careful. There are potential forces, and there are contact forces that have no potential. So you have to be very, very careful. Say, oh, I want to understand the Newtonian force. No, it's not possible. You have to specify the model. That's all I want to say. Sorry for the interruption.
No problem. That's fine. Good morning, Jesus.
Good morning. Good morning there.
And Dr. Sobchak.
Good morning. I can't understand to the meaning of iso unit, because and I think that this is too much important, because this define the number system, iso numbers that we are defining.
Yes.
Then if we can't understand that, then we can understand what are iso numbers. Then it is too much important. I try to think about the ideas of Professor Gareth Sobchak about the definition of iso unit, and he says that maybe iso unit is a constant. If it is a constant, then we are in the real numbers, in fact. No?
Yes. In some cases, when we work with iso numbers, the iso unit is a constant. But when we move to iso vectors, iso functions, iso curves, iso surfaces, and so on, then the iso unit is integral differential operator, which is positively defined and depend on many parameters, which is connected with the physical system. For instance, it can depend on the velocity, on the mass, and so on. But firstly, the first aim is to introduce what is the ISO number, to deduce some of their properties, to see the differences between ISO multiplication and the classical multiplication, and to investigate if the defined ISO numbers, the set of ISO numbers satisfy all axioms for a ring and for a field. And then I will start my lecture with definition of ISO numbers, basic operations of with them, and so on. And then I will finish this lecture with ISO vector, ISO line, and you will see the big differences, because as you can, in the end of this lecture, you will see that in the classical case, we have perpendicular vectors, orthogonal vectors, but in the ISO case, we have not orthogonality and the inverse. You will see the differences now in this lecture. Okay, I will start the lecture.
Can I ask just one question related to that? Is it correct that in the slides that we saw last week, all of the ISO functions that you illustrated of the different types were all isomorphic in the sense in which Dr. Sobczak mentioned in his brief note, so that all of the examples that you gave last week are actually isomorphic to ordinary functions, even though they were iso functions by definition. There is an isomorphism that maps them back into ordinary functions.
But see, not in any case we have isomorphism. There are cases in which we have isomorphism and cases in which we have not isomorphism. And I will give examples to the table when we have not isomorphism.
Perfect.
Okay.
Excellent. Thank you.
Okay, because previous week I know that this is only some introduction to what is Iso-Differential Calculus and so on. But now I will prepare in details all things, so that to understand
Dr.
and to see the
Sobczak,
difference.
did you have a question, Dr. Sobczak?
That when you differentiate, I think that's when you lose the isomorphism of the algebras, when you're differentiating the iso unit.
Yes, but see, we have cases. I think that in the previous lecture there are examples, cases in which the isotopic element is not differentiable on all set, but the isolift is differentiable.
If I may say, the physical profile in physics, we call them, when we have an isomorphism, we call it regular, in the sense that the isomathematics can be constructed with the non-unitary transformation. When you don't have an isomorphism, then we call this formulation irregular. The best illustration in this is the Lie algebra, in which the isotopy of the second Lie theorem imply necessarily that the so-called structure constant in Lie theory becomes function, and that cannot be obtained by non-unitary transformation of Lie theory. So therefore, it's a new, a bona fide, new realization of Lie's axiom. But this is what we do in physics, and mathematically, I do not know.
Excuse me, Dr. Santilli, you mentioned in one presentation that you made the past year the theorem of Poincaré, Bischoff, and Will. I think it is important to refer to that because I think that the building of the number systems that are constructed are related with this theorem. You present to us the past year this theorem, and I try to understand this, and I think that it is too much important in the definition of isonumbers.
Well, it is correct, of course, Dr. Cruz. I spent many pages in the second volume of my book with Springeville Lag, 1982 or 3, I believe. You will see there the Iso-Poincare-Birkhoff weight theorem is fundamental for every physical application, each and every physical application, because quantum mechanics is based on an associative envelope, which is characterized by the Poincare-Birkhoff weight theorem. Hadronic mechanics necessarily, to be axiom preserving, must to be a completion according to EPR, must be based on an associative algebra, but has to be iso-associative, otherwise it's trivial. Otherwise, it's part of the class of equivalence of quantum mechanics. There is zero novelty in my view. So yes, you are correct. However, the proof of the Iso-Poincare-Birkhoff weight theorem is relatively quite simple, and but again we remain with this not the difference in approach, in which you know, an infinite variety of iso units cannot be conceptualized. You see, I never tried to understand what it means Hilbert space in quantum mechanics, which is an infinite dimension. No, I never tried to even try to understand. No, what I care is that it did work. The infinite dimensional Hilbert space, they work very well, and that's why I use them for years and years. And exactly the same thing for the iso unit. Try to understand an infinite variety of different topologically inequivalent quantity you want to conceptualize in one single notion. No, it cannot be done. And in any case, not that much in physics. Well, and mathematically it may have some meaning, but physically, no. Physically, you look at the application, well, produce where the formalist produces number representation. That was the, at least it's I beg you, Dr. Cruz, this is my personal view with no expectation of pretension that you agree. It's just my personal view.
Okay. Anyway, I like, if possible, to see reference in the presentation of isonumbers to this theorem, because in my opinion, this can help to us to the understand of these number systems.
Okay, I think we probably should let Dr. Georgiev proceed with his intended presentation today. We'd also, just to mention, if I understood correctly, Dr. Georgiev, Georgiev, that you anticipate, continuing in a series of lectures of dealing with different subjects at different times. Is that correct?
Okay, thank you. So the main aim of the lecture today is to introduce isonumbers, the basic operations of isonumbers, then to introduce isopoint, isovector, isocoordinate system, then to introduce the basic operations with isovectors, and to see the differences between classical vectors and isovectors, and then to introduce what is isoline and what are the basic equations of an isoline, and to compare with the equations of the classical lines. So suppose that het t is a positive constant. With het I, we will take the inverse of this positive constant, het t, and then we define the set hat F of hat T in this way, which is, will be the set of all real numbers divided on the element hat T. This element hat T is the isotopic element. The number hat I, which is the inverse of the isotopic element, will be called the basic iso unit. The set hat F of hat T, which is obtained by the division of all real numbers by this isotopic element hat T, will be called the set of iso real numbers with basic iso unit hat I. The real number A is said to be the iso original of the iso number hat A, and the number hat A, the iso number, is said to be the iso lift of the real number A. We'll say that two elements hat A and hat B are equal, and we'll write in this way if the corresponding iso originals are equal. So by the properties of the equality of the real numbers, we have the following properties of the equality of the elements of the set of iso numbers. Firstly, every iso number is equal to the same iso number if the iso number hat G is equal to iso number hat A, and then hat A is equal to iso number hat G. If hat G is equal to hat A and hat A is equal to hat L, then hat J is equal to hat L. We have transitivity properties. The basic operations iso addition and iso multiplication between iso numbers will define in this way. So as an example, if we consider and we take the isotopic element to be equal to 2, then the basic iso unit will be equal to 1 over 2. The iso addition of the iso number 3 and iso number 4 is equal to iso number 12. In the classical case, 3 plus 4 is equal to 7. This set of iso numbers satisfies all axioms for a field. In other words, the sum of two iso numbers belongs to this set of iso numbers. The iso multiplication of the iso numbers is again iso number. We have the associativity property for the iso addition, given as fourth property for this set hat F hat T. We have the associativity property for the iso multiplication, given as fourth property. We have the commutativity for iso addition, commutativity for iso multiplication. Here, the iso-neutral element, which is denoted by hat 0, it coincides with the classical neutral element. But when we have iso multiplication, the iso-neutral element is the defined iso unit. Of any iso numbers, there is the iso number minus hat F, for which the sum of hat A and minus hat F is equal to the hat 0. If the iso number is different than 0, then it has iso inverse numbers, and its iso multiplication with the iso number hat F is equal to the iso unit, not the classical unit, is equal to the iso unit. Also, we have the distributivity law for the iso multiplication and iso addition. If hat J is different than 0, then we define iso division in this way. And the element het F plus minus het J will be denoted in this way. In other words, isodivision and isosubtraction operation exists in the definite field het F, het T. For any three elements het F, het J, het H, which belongs to the set het F, het T, we define the iso addition of three elements.
I have one question.
Yes.
Why are we going through all this when we know that the iso real numbers are isomorphic to the real numbers? Does all these properties follow immediately from the relationship of the addition and multiplication without having to go through all this?
Yes. In this case, because
of course it's true because the algebras are isomorphic.
Yes. In this case, because the iso unit is a constant, we have isomorphism. Okay.
Yeah. Okay. But
okay.
It's really pretty trivial what we're going through now because they're isomorphic. As algebras are isomorphic, so of course these rules all follow directly.
And then we define, using this definition, we can define the iso addition of 4 elements and iso multiplication of 4 elements. Also, if het R is a solution of this equation, then it is a solution of this equation for any other element het H, which is iso number.
Okay.
Next, yes.
I mean, just attract the attention, Dr. Georgiev, of course, is correct, but there is one point that I believe is important for application, and namely not only the associativity of the iso product, but also what you correctly recall, which is in my original paper in 1993, and which is the isocommutativity. And when those are the reason why iso-octonion do not exist. They cannot be formulated consistently. You violated the axiom. So everything is correctly, as you stated, Dr. Georgiev, correctly real, complex, and quaternionic number. Yes. Octonion, no. This is my original paper in 1993.
Okay.
Even in detail, volume 1 of my Elements of Hadronic Mechanics.
So next, the iso-real number het I is a positive iso-real number. It is proved in details. Then we will say that an iso number het J is less than to the iso number het H, and to write in this way if their iso difference is a positive iso-real number. Here I will give an example. If we take for isotopic element to be equal to 4, and if we consider this equation, then the solution of this equation is equal to x is equal to 1/3, and the corresponding solution is 1/12. If we take as isotopic element het T to be equal to 5 and consider this equation, here the multiplication is the standard multiplication. In the previous example, we have iso multiplication. Here is the classical multiplication. Then the solution of this equation is 25/3. This solution does not coincide with the, if we consider this equation as in the classical case, because in the classical case, the solution will be 5/3. Here, in the iso case, the solution is 25/3. So when we say that an iso-real number het J is less than or equal to the iso-real number het H, we will write in this way. Then this difference between het H and het J is positive iso-real number or is equal to the iso 0. For every two iso-real numbers, we have one of the following possibilities. If they can be equal, or the first can be greater than the second, or the first can be less than the second iso real number. The iso real number head J is a positive iso real number if and only if it is greater than the iso 0, 0. If head A, head B, head C, head D are four iso real numbers for which we have the following relations, that head A is greater than head B and head C is greater than head D, then the sum of head A and head C is greater than the sum of head B and head D. Also, if head J and head H are two iso real numbers, and head J is greater than head H, then the sum of head J and head L is greater than the sum of the head H and head L. If head J, head H, and head L are three iso real numbers, so that head J is greater than head H and head H.
Yes. Comment that your inequality challenge, shouldn't that be with a hat over it? Because, for example, if the iso unit is a negative number, in real numbers it would reverse the inequality. So it should be distinguished from the ordinary greater than sign by a hat over it.
But see, we have supposed that the isotopic element is a positive definite element. In the case of iso numbers, we have that this is positive constant. But when we have a negative definite unit and negative definite constant, then we obtain the so-called iso-dual mathematics. But it is very early to speak for the iso-dual mathematics when we have the inverse sign. Okay,
yeah, that's clear.
Okay. Absolute value or modulus of an iso real number head J is called larger or than the iso real number of the iso real numbers head J and minus head J. For the definite modulus, we have the following three properties: that the modulus is always non-negative iso real number, and we have that the modulus of an iso number is greater than plus minus of the iso real number head J, and the modulus of head J and minus head J is always equal. Also, we have the following inequalities for the modulus of sum and the differences of two iso real numbers. The first inequality is given with this inequality, the second one with this one, the third one is given with this one. When we have iso multiplication, then the modulus of iso multiplication is equal to the iso multiplication of the corresponding iso modulus. The iso division of the modulus is the equal of the modulus of the iso division. And if modulus of some iso real number is less than the iso real number head H, this is held if and only if we have the following two inequalities for any iso real number which is a positive iso real number. Here I will give an example in the case when the isotopic element is equal to 2. If we consider this inequality, 3x minus 4 is greater than iso real number 5. In the classical case, we get that x is greater than 3. But in the iso case, after we follow all rules for the iso multiplications and for the iso division, we get that head H is greater than head 6. We have difference with the classical case. As next example, if we consider as isotopic element to be equal to 4, and if we consider this inequality, in the classical case, the solution of this inequality is x less than 1. And in the iso case, we get that the solution is less than 1. So we have again two possibilities. In the iso case to coincide as in the classical case, as in this example, and in the iso case to be different than the classical case as the previous example or this example. Here the solution is x greater than 3. In the iso case, we get that the solution is x greater than 6. We have given a definition for modulus of iso number, but we define an isomodulus of iso number, and isomodulus of iso number we define in this way. In other words, the isomodulus of the iso number hat h is equal to this one. And here is an example. If we consider the isotopic element to be equal to 4, the real element to be equal to 3, its modulus is equal to 3. But the isomodulus of this iso number is equal to 3 over 16. There is a difference in the isomodulus. If we take as an isotopic element to be equal to 6 and the real element to be equal to -6, the classical modulus is equal to 6, but the isomodulus is equal to 1 over 6. Again, we see the differences between isomodulus of iso numbers and modulus of iso numbers. If we get consider next example as the isotopic element to be equal to 5, the real element to be equal to -10, then the classical modulus is equal to 10, but the isomodulus is equal to 2 over 5. We see again differences. Now they are given some of the basic properties of the defined isomodulus. Again, we have that the isomodulus is non-negative. We have the triangle inequalities, and we have homogeneity when we have iso multiplication. The isomodulus is different than the modulus classical, but the isomodulus has the same 3 properties as the classical modulus. We have a need of this isomodulus because in the case n is equal to 3, the 3-dimensional case, 4-dimensional case, and so on, we define distance between 2 isovectors. And to be consistent, this definition with the 1-dimensional case, we have a need of the definition for isomodulus. We see that it is different than the classical modulus. Then we define iso square in this way, iso power 3 in this way, and
Excuse me.
yes.
Question.
Yes.
Then we can define one operator, the operator head. And
Yes.
This means to multiply by the unit.
Yes, yes, we can
Yes.
define such operator.
And
Yes.
then we go back to the real numbers here, only
Yes.
using that operator.
Yes, yes. Then we have isomorphism.
Okay, okay.
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 Mhm.
Then we define this is iso power in this way, and this is the classical power 2, 3, and so on, n. In the case when we have iso square, we get this number, and iso power k, we get this number. When we have classical square, we get this number, and when we have classical power k, we get this number. Here are representation of the iso power in the case when we have real number x, which is given in this way, and the power k, which is given in this way. For x, now we have given a definition when the power is a natural number. Here we generalize this definition when the power is arbitrary real number, and the definition when the power L is arbitrary number is given in this way. The power L iso power is here. Here the power is the classical power L. We see again differences. And here we have real number x of iso power L, then it is equal to this one. We have differences between the defined three powers: iso power of iso number, classical power of iso number, and iso power of real number. So I will give an example. In the case when the isotopic element is equal to 4, so we will compute this in the iso case. In the real case, it is equal to 40. This number, if we consider as real number, is equal to 40. But in the using our definition for iso power and iso real number, we get 133 over 4. This is in the iso case. In the classical case, as you can compute directly, 3 power 3 plus 3 square plus 2 square is equal to 40. In the iso case is 133 over 4. We see differences between the classical computations and the iso computations. So now so far we have considered the one-dimensional case. Now we will consider the n-dimensional case. So for one-dimensional case, we have a need of only one isotopic element. For n-dimensional case, we have a need of n isotopic elements. These isotopic elements, they can be different, but they can coincide. So in the n-dimensional case, we define iso n-dimensional number or iso point in this way: x1 over het t1, x2 over het t2, xn over het tn. We divide all components with different isotopic elements. So the elements of the defined set are called iso points. The numbers xj over het tj are called JIT iso coordinate of these iso points. All points of this kind, where all elements are equal to 0, but only one xj over het tj is different than 0, is said to be JIT iso coordinate iso axis. The iso point 0, 0, 0 is said to be the iso origin. It coincides with the classical origin. The number n is called the dimension of the defined set. This point x is said to be the iso original of the iso point defined in this way. And the iso point is said to be the iso lift of this real point given in this way. So as an example, if we consider the case when n is equal to 3, the first isotopic element is equal to 2, the second isotopic element to equal to 3, and the third isotopic element to be equal to 7. And if we take the real point -1, 2, 4, then the iso lift is given in this way. If we take the 4-dimensional case, or n is equal to 4, isotopic element, first isotopic element to be equal to 3 over 2, the second isotopic element to be equal to 2, the third isotopic element to be equal to 3, and the fourth isotopic element to be equal to 5. And we take, if we take this real point 2, 1, 5, 6, then its iso lift is given in this way. And next example is the two-dimensional example. For the first isotopic element, we take 7/8, and the second 9/4. For the real point 5,6, we get this iso point, which is given with this expression. Here is given example if we have a real point x and iso point x to find the corresponding isotopic element. This then, if we get this real number to be this one and iso real number to be this one, then we can find the corresponding isotopic element. In our case, the first one is equal to 18, the second one is 1/2, and the fourth one is equal to 1/2. Here is next example when we know the real point and the iso real point to find the corresponding isotopic elements. And it is given the fourth example. Again, we know the real point x and the iso real point hat x to find the corresponding isotopic elements. Now it is very important because we will define iso distance between two iso points in the defined set. We define iso distance between two iso points with this quantity. Here participate all these isotopic element hat Tj, and here participate the basic isotopic element hat T. When hat Y is equal to 0, then we get the iso norm of the iso real point hat X. So now we'll give very good examples. First example is in the two-dimensional case when the first isotopic element is equal to 2, the second isotopic element is equal to 4. We take two real points 2, 3 as x, and the second real point y equal to 3, 4. The classical distance is between these 2 points x and y is this one. But the isolift of x is given in this way. The isolift of y is given in this way. And the iso distance between the hat x and hat y is this number.
Before you
this
change,
number is with different change with the classical distance. Yes?
Yeah, just a quick question, just to show I'm still listening here. On the first line of the slide, you have t hat equals 6, and I don't quite understand its role there. Is that a typo? Or?
No. See, when we work in the n-dimensional case, we have as the distance is some iso-real number. And when we work with the iso-real number, then we were in the one-dimensional case, in the previous case, when we have other iso unit hat t. Because when we have iso inner product, for instance, we will see later, the result is iso number. But if we take iso addition of two iso inner products, then we move to the one-dimensional case, and in the one-dimensional case, we have other isotopic element given with hat t. All of these isotopic elements can coincide.
Oh, I see. Okay, so so t hat without the subscript is in a different space, is one-dimensional.
Yes. Because when we get, for instance, iso distance between two dimensional iso points, we have two isotopic elements, but the iso distance is iso real number. Then we go in other space. For this space, we have separate isotopic element, which is given with hat t.
Okay.
And it is possible all of this to coincide and all of this to be equal to 1. when they are equal to 1, we get the real case. Okay.
Yes.
Well, I just mentioned to Dr. Page as well as the other colleagues that this is what those n-dimensional numbers. That's what we use to at least initiate some new application in biology, where there is multi-validness.
Okay. So as next example, we'll consider the three-dimensional example. Here are given the isotopic element. We take two real points x and y. The classical distance is this one. The isolift of x is given with this one. The isolift of y is given with this one. But the isodistance is this isoreal number. This number is very different than the classical distance. And I have prepared a third example. The third example is again three-dimensional example. We take for x to be this real point, for y this real point. The classical distance is given with this number. The isolift of x is this one. The isolift of y is this one, and the isodistance is this number. This number is different than the classical distance. So after we have defined the basic operation for n-dimensional isopoints, we define addition between them in this way. Isomultiplication with iso number or real number in this way. Iso-difference defined with this equal 1. Yes. So example, we consider a three-dimensional case. We take as isotopic element to be this one, real points x and y to be this one. Then their isolifts are given with this way. The isomultiplication with the isopoint x with the number 3 is given in this way. And the iso-addition has the following expression. So we see that the classical addition between x and y is different than the iso-addition when we consider them as iso numbers. Also, the multiplication, classical multiplication of x by 3 is different than the iso multiplication. Because when we have the classical multiplication here, we'll have -3, 6, 9. Here we have -3 over 2, 2, 18. Very different. So here is given a second example. Two-dimensional example. We take for isotopic element the first one to be 4, the second one to be 3, as real points to x and y to be this one. Then their isolifts are given in this way. The iso inverse of the isopoint y is expressed with this isopoint. And here we find the iso multiplication of hat x multiplied by 2 and iso addition with minus hat y has the following expression. Here is given as fourth example, a four-dimensional example. We have 4 isotopic elements. For the real points, we take x and y to be this one. Then the corresponding isolifts is given with these isopoints. The inverse of the isopoints hat x is given in this way, and it is very different than the inverse of the real point x. Here is given an expression of minus hat x plus 3 iso multiply by hat y, and it has the following expression. Now we'll deduct some of the properties of the defined two operations in this set hat F, hat T1, hat T2, hat Tn. So that to show that the defined set satisfies all axioms for a field, we take three iso element hat X, hat Y, and hat Z, and two numbers alpha, beta. Then we have the commutativity for iso addition.
Excuse me.
Yes.
I have a question in the before slide. Because how I understood when you use one operator plus product or anyway, you are using a different unit with that operator.
So in this case, we will consider not one-dimensional operator. We will consider n-dimensional operator. First coordinate will be the first operator plus the corresponding element, second operator plus, and then the general operator for the isomorphism will be with coordinates.
Okay. Inside parentheses, we use the normal plus.
Yes.
The conventional plus. Okay.
Yes.
Okay. Thanks.
Okay. Next property of the definite operations is the associativity of the iso addition, existence of iso-neutral element in the n-dimensional case, existence of the iso-inverse element with respect to the iso addition, existence of neutral element when we have iso multiplication, the associativity of the iso multiplication, distributivity of iso multiplication, and iso addition we have again. Then by these properties, it follows that we can consider the defined set as a vector space. In this case, any iso point, which is defined as x1 over hat t1, x2 over hat t2, and so on, xn over hat tn, is said to be an iso vector, and the numbers hat j are said to be its iso coordinates with respect to the isobasis, which is given in this way. Here in the isobasis is not the classical unit 1. Here is 1 over hat t1, and so 1 over hat t2, and so on 1 over hat tn. Now we'll define iso inner product. If we take two iso points hat x and hat y, then iso inner product of hat x and hat y is defined with this expression. It's given in this one. Here we give iso square, which is given in this way. And now we give a relation between the power of the iso square and the iso distance. So now I will give example. First example is in the three-dimensional case. We take two real points x and y. Their isolifts are given in this way. Then their iso inner product is equal to 18. It is very different than the classical inner product. As next example, we consider the two-dimensional case. We take again two isotopic element, one to be equal to 4, the second one to be equal to 3. Two real points x and y, their isolifts is given in this way. Then the corresponding iso inner product is equal to minus 22. And as fourth example, we consider four-dimensional case. Again, we take four isotopic elements, two real points x and y. we find their isolifts, which are given in this way, and the iso inner product of these iso points is equal to -2, different than the classical case. We say that two isovector x, x, and x, y are iso-orthogonal if their iso inner product is equal to 0. We will write in this way. The classical case, if we consider the classical basis, then we have the classical orthogonality and iso-orthogonality. But in the next examples, we'll see differences. So let us consider two-dimensional case as the first isotopic element to be 1/2 and for the second isotopic element to be 1/3. We take two real points x and y. These real points, their inner product, classical inner product, is equal to 0 and they are orthogonal in the classical case. But the isolifts of the considered real points x and y for the first point is -6, 3. For the second point is 2, 6. Their iso inner product is equal to 3. It is different than 0. In the classical case, we have that it is equal to 0. Then in the classical case, they are orthogonal. But in the iso case, their iso inner product is equal to 3, different than 0. Then in this case, we have not iso-orthogonality. So in the next example, in the red color are given the real cases. But in the green color are the iso cases. We have not orthogonality in the iso case. As we see the green case, real case, we have orthogonality. This is the red case. So as next example, we consider a two-dimensional case. As the first iso point, unit, we take 1/4. As the second isotopic element, we take 1/2. We take two real points x and y, these real points. Their inner product, classical inner product, is equal to 6. And in the classical case, they are not orthogonal. But the isolifts of these points, x and y, are given with these expressions. Hat x is equal to 8, 6. Hat y is equal to -12, 8. Their iso inner product is equal to 0. Then in the iso case, they are iso-orthogonal, but in the classical case, they are not orthogonal. In the red color, we see the classical case, not orthogonality. In the green color, we see the iso case. We see difference as pictures and difference as computations. 6, 0. Here, red is the real color, is the real case, excuse me, and green color is the iso case. So as next example, we'll consider a three-dimensional case. We take as first isotopic element to be 1/2, as second isotopic element to be 2, and as third isotopic element to be 4/11. We take two three-dimensional real points x and y. Their classical inner product is equal to 0. Then in the classical case, they are orthogonal. But their isolifts is given in this way, and their iso inner product is equal to 0. So in this case, in this example, we saw that we have orthogonality, classical, and iso-orthogonality. The picture is this one. So we have possibilities: orthogonality, iso-orthogonality at the same time, to have iso-orthogonality but not orthogonality in the classical case, and to have orthogonality in the classical case and not iso-orthogonality. These three examples. So now we'll give some of the basic properties of the defined iso inner product. For these properties, we take three iso elements, hat X, hat Y, and hat Z, and a number alpha. We have as first property that commutativity, second property that the iso square is greater than 0. We have transitivity, homogeneity, and next property is that if the iso inner product of two elements is equal to 0 for any iso point hat X, then the iso point hat Y is equal to 0. We have iso Cauchy-Schwarz inequality given in this way. Now we take m elements, x1, hat x1, hat 2, hat x2, hat xm, and consider the corresponding their isolifts, which are given in this way. Then we say that the isovectors hat x1, hat x2, and so on, hat xm are linear isodependent if there are constants alpha 1, alpha 2, and so on, alpha m, so that this m-tuple alpha 1, alpha 2, and so on, alpha m is different from 0, 0, 0. And we have the following equality. So the expression for the linear isodependence in the taus is given with these computations, or with this system, or with this system. So in this case, we have equivalence between the classical dependence and the isodependence. As next example, the system of m iso points or isovectors is said to be an isoorthogonal system if hat j is isoorthogonal to hat xk, in the case when j is different than k, and iso-orthonormal system if the iso length of all of these isovectors is equal to the iso unit. Note that not equal to the classical unit, equal to the iso unit in the space hat F. So any iso-orthonormal system in the set hat F, hat T1, hat T2, hat Tn is said to be iso-orthonormal isobasis. Any system of n isovectors that are linear iso-independent is said to be isobasis in this set hat F, hat T1, hat T2, and so on, hat Tn. Since not any orthogonal system in the classical space Rn its isolift is isoorthogonal in this space hat F, then there is not equivalence between the bases in the classical space Rn and the defined space hat F, hat T1, hat T2, and so on, hat Tn. So now we'll give the following example. Consider two-dimensional case. As isotopic element, we take 1/2 and 3/2. We take these two real points. Their classical inner product is equal to this number, which is different than 0. Their isolift is given in this way. And their iso inner product is equal to 0. This system is linear iso-independent, and then the corresponding isolift is an iso-orthonormal isobasis. Here is given an expression of any iso element using the isobasis hat x1 and so on hat xn. Now we will move to the iso line. Isolines, firstly, and in this lecture, we'll consider in the two-dimensional case. So we start now with the so-called isoplane, iso-analytic geometry. Suppose that head T, head T1, and so on, head T2 are positive constants. Take real point V is equal to V1, V2. Head 2 points P and Q. Then their isolifts is given in this way. We define this set, which is given in this way. Here participate the isotopic element of power 2 and the second isotopic element of power 2. Then the set of all iso points for which this iso difference belongs to the defined before seconds, this iso set will be carried an iso line through the iso point head P with iso direction, iso vector head V. So in the next example, in the red color, is shown the classical line through the point P with direction vector V. And in the green color is shown the isolift in the case when head T1 is equal to 1 over 2 and head T2 is equal to 1 over 2. In the red color is the classical case. This is the classical line. In the green color, this is the iso line. So we have the following terminology when and the following phrases when an iso line head L and iso point belongs to the iso line, or iso line contains other iso point head X, or head X lies on the iso line head L. Iso line L passes through the iso point head X. Head X and head L are incident. Head X is incident with head L, and head L is incident with head X. So a fundamental property of an iso line is that it is uniquely determinate of two iso points, that line complete. If head P and head Q be distinct points, which belongs to the set head F, head T1, head T2, then there is a unique UZ iso line through these iso points head P and head Q. Now we start to define the case and to give a definition when an iso point lies between two iso points head P and head Q. An iso point head X lie between two iso point head P and head Q. If we have the following expression of the iso point head X, or the following isolinear isocombination between head P and head Q. Now we give an example. We take 2 points P and Q and the real point X. This real point is between P and Q. Then their isolift is given in this way. And the isolift is again is between the head P and head Q. Here in the red color, we see that and in the blue is given the head the point X, and in the red color is the classical line. In the green color is the iso line. Here is the point head X. Its iso original is given in this way. The distance between the point X and the final point here is different than the distance between X and here the final point. So as next example, we take for P and Q to be this one, for isotopic element to be 2 and 4 respectively. For the point X to be the point 1, 3. It is between the point P and Q. For isolifts, we have the following representations. the picture is given in this way. Here we have the distance between the point X and the final point, in this case P, is this one. This is the classical distance, but the iso distance between X and the head P is this one. It is very different. So in the next example, we take other combination of isotopic elements. Then we see here this example shows that the point X does not, it is not between the point P and Q, and the corresponding isolift is not between the point P and Q. So if two isolines passes through the isopoint head P, then we say that the isolines intersect at head P, and head P is there at intersection isopoint. If three or more isolines passes through the isopoint head P, we said that the isolines are isoconcurrent. If three or more isopoints lie on some isolines, we say that the isopoints are isocollinear. Now we'll give the basic expression of the equations of the isolines. Firstly, if we take a vector V, classical vector V, then its isolift is given in this way. Then if we define the vector head V in this way, we have that the above vectors are orthogonal. Iso-orthogonal. Here are given different pictures when we have different isotopic elements for the iso direction V, and this is the isonormal vector of the corresponding line. As picture in green line is given the iso direction of the isoline. Here is given the isonormal of the isoline. In the next example, we take this combination of isotopic elements. Then in this picture is given that this is the iso direction. This is the isonormal vector. So the angle between the iso direction and the isonormal vector is different, and this angle, as we see in the next lecture, depends on these isotopic elements. In this case, we have this angle. In the previous case, we have this angle. And as fourth example, we consider as combination for the isotopic element to be this one. Then the iso direction vector is given with this expression, and its isonormal vector is given with this expression. And they are shown in this picture. Again, we have different a different angle. This angle, I know that it depends on the isotopic elements head T1 and head T2. And in the next lecture, we see this dependence, and this dependence will be deducted with exact expression. So we have defined iso direction of an isoline in the two-dimensional case, and isonormal of an isoline in the two-dimensional case. Then the first equation of the isoline which passes through the point head P, head Q, with iso direction vector head V1, head V2 is given with this expression. So in the classical case, we have not these elements head T1 and head T2, but when we have iso case, the isotopic elements act on the corresponding equations in this way. And then it is very usual to say that the line and isoline are different, because when we have this isotopic element is different than one, we get different lines. Now it is given as first example, we take the point P, 1 minus 1, isotopic element to be this one. The vector V to be 2, 3. The classical line has the following equation, but the iso line have the following equation. We have differences between the equations of the classical line, this one, and the equations of the iso line, which is this one. And in the next picture, in the red color is given the classical line. In the blue color is given the iso line. As next example, we take for the point P to be 0, 0, isotopic elements to be 1/4 and 1/2. For the vector direction vector, we take this vector -1, 2. The equations of the classical line is this one, but the equations of the iso line is this one. Again, we have differences because here the isotopic elements act on the iso line. In the next picture here, in the red color, is given the classical line. In the green color is given the iso line. Here the angle between the classical line and the iso line is this one. In the previous case, this one, the angle between, this is the classical line, this is the iso line, the angle is this one. Again, the angle, I know that depends on the isotopic elements, and in the next lecture, with big details, we'll be explaining why and how these isotopic elements reflect on the angles and for the other things. And then this is the first example. We take the point P11, the isotopic elements to be this one, direction vector to be this one. The classical line equations are given in this way, but the iso line, the equations of the iso line are is this one. This equation is different than this equation. In red color is given the classical line, in green color is given the iso line. If we consider the angle in this direction, the angle is very big. But the isotopic elements are very small. In the next lecture, we investigate how this angle increase and decrease depending on the isotopic element head T1 and head T2. So now we define this iso vector. Then we give an example because in the classical case, in the classical analytic geometry, we have equations through for a line through a point and with direction vector, and equations of the two-dimensional line through 2 points. Now we will consider the iso case, iso line through 2 points. So now we consider 2 points P and Q. This will be the isotopic elements head T1, head T2. The vector with ends P and Q, classical vector is 3, 1. The iso vector is given with this way. This iso vector is different than this vector. And in the red color, red color is given the classical vector PQ. In the green color is given the iso vector. As we can see, and as we can expect, the length of the corresponding segment will be different. And these differences between the lengths of the segments will depend again of the isotopic element head T1 and head T2. So as next example, we take these points P and Q. The corresponding classical vector PQ is this one, but the corresponding iso vector is this one. Again, we see differences. As you can see, we have not linear combinations between the there is not a real number, so that multiply by classical vector to get the iso vector. Because if we multiply by 4 here, we get minus 32. But 4 multiplied by minus 2 is minus 8, which is different than this one. They are not classical proportionally, the classical vector PQ and the corresponding iso vector. So here in the red color is given the classical vector, and in the green color is given the iso vector. We see here that the length of this segment is less than the iso length of this iso segment. In the previous example, it was the conversely. So, and next example, we take for the points P and Q to be these points, isotopic element to be this one. So in the previous cases, we have considered combinations, small isotopic elements and large isotopic elements. Here we have small isotopic element and greater than one isotopic elements. And now we will consider what happens. The classical vector PQ is this one. The iso vector is this one. And in the red color is given the classical vector, and in the green color is given the iso vector. Again, we see differences. So here are given the explicit equations for iso line when we have 2 points P and Q. They are given in this way. Again, here we have the influences of the isotopic element hat T1 and hat T2. This and this one. So, thank you for your attention.
Okay.
Thank you very much.
The main aim of this lecture is what is isofield and isovector and isoplanar geometry. In the next lecture, we will see the differences between isocircle and classical circle, isoparabola and classical parabola, and the basic their properties. There depends on the isotopic element. Okay, thank you.
I have one question, I guess, a kind of summary sort of question that everything that you've shown today looks to me to be entirely expected from the underlying sort of isomorphism that Dr. Subject mentioned earlier. I guess maybe Dr. Subject is no longer here.
Yes.
But I'm just wondering if there is some something that you could highlight that makes these iso fields distinguished in some way. Because maybe I should add that my question is motivated by thinking of geometry in a coordinate-free manner, in an intrinsic manner, so that the fact that in what I see here mostly looks like transformation of coordinates, so that I can express the same geometry in, say, an oblique coordinate system as I can in an orthogonal sort of coordinate system. And so that I'm just wondering if you could highlight what is different here about an iso field and somehow unexpected, perhaps.
Yep.
So, yes, please.
Well, why don't you present? After I would like to clarify indicate one physical application of what you've done. Go ahead, Dr. Georgiev, please.
We see that we have not, firstly, when we solve the equations, the examples with equations and the inequalities, we have very different solutions in the real case, real field, and in the iso case. So there are examples in which in the real cases, we have not solutions of the corresponding equations, but in the iso cases, we have solutions. And the same it happens when we have inequalities. So some of the inequalities which are very different and very difficult to be made in the real cases, we can transform, isotransform in a very simple form. And using the isomorphism, for which we speak and mentioned here, we can, from the simple form of the iso equation, we have give what is the behavior in the real cases. Okay.
Yes, maybe some examples of that, I think, would provide greater motivation, I think.
But yes.
Make an example in which we have done many measurements. Very quickly, I believe, as we all agree, that special relativity, the Minkowski space-time is absolutely perfect. It's exactly valid for the way conceived by Einstein. Let me clarify, namely for point particles and electromagnetic wave in vacuum. And that's so why we've spent decades in studying the isotopy of the structure. Well, because there are engineering implications which are not trivial. So for instance, the case in which the treatment presented by Dr. Georgiev is mandatory, it's a quantitative, more accurate representation of the behavior of light within Earth atmosphere. But here is the dramatic difference between Earth atmosphere and the Minkowski space. The Minkowski space is homogeneous and isotropic, and the Earth atmosphere is inhomogeneous because the density decreases with the elevation, and above all, anisotropic because the Earth rotates, and so therefore the medium rotates. So the question is, what is the correct definition? First of all, sorry, with all due respect, the use of Minkowski space-time is excessively approximate, because all the three directions, 1, 2, 3, are the same, and the index of refraction is assumed to be 1. But that's okay in the empty space. But I'm sorry, I cannot consider it until when it's presented as a first approximation. No, that's okay. But if it is presented as a final reality, no, that I cannot accept. But then let's go now to the how do we represent the light propagating in our inhomogeneous and isotropic, and is at that point in which the presentation by Dr. Georgiev becomes mandatory. If you want to do it correctly, you need 4 isotopic elements, 1 per each direction of space, and the 4th isotopic element necessarily for the 4th component for the index of refraction, because it is well known that the index of refraction of light in a physical medium is different than in space. So now, more precisely, we did this originally with 1 single 4-dimensional isotopic element in which you have 3 different T, 1 per each direction, and then the 4th is the isotopic element for the index of refraction. That is that was a first approximation. That's what we call iso-Minkowski space. However, I want to indicate that the correct mathematical formulation is what has been presented by Dr. Georgiev, namely with working individually, the space becomes multi-valued. Now, now we have done, I was mentioning that we have done a large number of measurements by using the most accurate available wavelength analyzer, the Yokogamat from Japan. We had to rent them because it was too expensive, and because basically what it turns out that the light loses energy when propagates within cold medium, in particularly when it is inhomogeneous and isotropic. And that is we did this. Actually we did systematic measurement of sunlight from the zenith all the way to the horizon. Measurements were done in USA on the east and west coast, as well as done in an island in Cyprus during one of our meetings. And it turns out that, as predicted, that from the way down, light is immediately very quickly absorbed. This is nonsense in Newton. Absorption is proportional to the wavelength. And then, but then why the sun is red at your eyes? Those measures showed very clearly that it was an iso redshift. Namely, you have an experimental visual verification of this mathematics that you have seen. Namely, the redness at sunset is, since the red light is absorbed way up when you begin the azimuthal angle starts, you know. But so the only conceptually the only solution is that the blue light of the sun at zenith is redshifted all the way to the to the red. This was done systematically. There are several papers that have been published. Incidentally, on historical grounds, this is a confirmation of Zwicky Tare light. And Zwicky proposed in 1928, I believe, hypothesis that the galactic light, the light from galaxy, loses energy to the intergalactic medium, which is hydrogen, very cold hydrogen. And he called this Tare light. And this is basically an experimental verification on Earth of this Zwicky hypothesis we have presented. But practical application, this has been used to try to come up with a medical equipment without to do operation without cutting the skin. The idea is to have a laser. This was an industrial, one of the industrial applications. I believe is under development in Europe now, is a laser with controlled frequency. Two lasers, one with controlled frequency actually, because they have to intersect underneath the skin. And but in one laser, the ray, you know, is basically goes through a tube which has the capability of changing the pressure of the gas to influence the frequency, but also to increase the temperature or to decrease to go way below the boiling and way below the freezing. And then if you have two of those rays that intersect in one point, then the frequency of those two frequency variable laser essentially go into resonance. And so in principle, it has never been tested, but the machine is being constructed now, I believe. Namely, there's a possibility that intersecting the laser ray that will intersect in our body without cutting the skin, Suppose there is a cancer, then those intersecting rays can excite so much that can cook, essentially cook or burn, if you want, depending on the frequency, burn the tumor and only the tumor, because those are very localized. And then there are other industrial applications that are all depending on different isotopic elements for each of the four different necessary aspects for an isotopy of Minkowski space.
I like to make a question and a comment. I understood the transformation of vector from one real space to one ISO space, no? And then we need only to use one operator that is a matrix and that in the diagonal have the units.
It's the first
Yes.
for for each dimension. Then this is the same. This is the same that we can use to do when we study continuum mechanics. It's the same. When the system is not isotropic, then you have to you can study the system with one transformation in this way. But I think that it is more interesting here is when in the definition of module, for example, in the slide HT3, you are using systematically the mapping of the head operator to the elements of the algebra. You are in fact using that. No, HT3.
8.3.
H3, yes, please, excuse
Slide
me.
8.3.
H3.
83.
Ah, 83. Yes, okay.
83. Okay, excuse me.
Yes. Wait. This one.
Yes, this one. You are defining. Okay, this is one example, and the slide before you are defining the module of Y.
Yes.
And then you are doing here. You don't map the head operator to the numbers, but only to the product.
So I have explained that in the n-dimensional case, every coordinate, the first coordinate belongs to the first coordinate corresponds the first isotopic element, to the second, and so on to the nth isotopic to n coordinates nth isotopic element. When we have iso inner product, then as a result we get as a number, but this number belongs to space which depends on this iso unit. It depends on this basic iso unit 1 over head t. And then because this is iso number, but does not belongs to the set with isotopic element head t1, head t2, and so on, then it depends on other space with basic iso unit 1 over head t. And this is the reason for which, for instance, when we have, if we have find the addition between the isomodulus of head x and isomodulus of head y, then for this iso addition we will use, because they're in this number as isomodulus is in this space head f head t, this is in the space head f head t, then we will use the isotopic element head t for their iso addition and iso multiplication.
I would like to make one comment on Dr. Cruz. What you indicate is, of course, correct. There is a great similarity with fluidodynamics. Yes, indeed, because the objective is the same. We have different parameters, different value, different direction, and so on. However, allow me to bring your attention on the preservation of this is a point. It's an axiomatic point that we discussed in the past several times, namely the beauty of quantum mechanics is to predict the same number under the same conditions at this different time. And that is the crucially dependent on homogeneity and isotropy of space. The moment you exit from that, which is the case of fluidodynamics, you absolutely lose that that feature. So with all due respect, personally, when I exposed to an experimental number in fluidodynamics, I consider certainly it's physically value. My God, I beg you, knowledge, acquisition of knowledge, little step by little step. So, but I consider it a Polaroid view of the characteristics. I cannot accept it as, or at least I have doubts as having that prediction remains over time. No, because you don't have the structure for the invariance of numerical value. So the mathematical formula is so beautiful presented by Dr. Georgiev is that if you look at the axiomatic aspect, yes, since it's an isotope, yes, you do preserve the numerical prediction over time, because of that's precisely the function of isomathematics. That's the best illustration is in an isogeometry. Why isogravitation? Why we are so much interested in gravitation? Because general relativity is covariant. And again, I can accept an experimental, I can accept it only a Polaroid picture. I'm sorry, I respect it, a beautiful experiment. But I cannot see that the prediction is invariant over time. Besides being dependent on each experiment has a different method, but that's another story. So, but when you do reformulate, you use exactly Einstein field equation, no change. You use Einstein field equation on the iso-Minkowski space. So then you have an invariance on the isopoincaré symmetry, and then it's very easy to prove that numerical prediction are preserved over time. So the experimental, let alone axiomatic implications are rather serious, and at least that's my view.
But my comment and question was because how you can see in the question that in the line that is over the mouse point, you are mapping the operator head to the product and to the numbers, to the real numbers. You are speaking about two real numbers, alpha 1 and alpha 2, and then there is a mapping of here from the head. Yes, this equation, and then you are mapping the head operator to the product, and then you are using x1 head and x2 head for this, for this operation. Then I am trying to understand the ISO numbers like a mapping of the head operator to the all the elements of the algebra. This is
yes, I understand. So then I have to prepare in details investigation the map between this ISO field and the isolated algebra. Okay.
Yeah. Yes.
Okay.
Yes.
Yes. And I will prepare this for the next seminar, because I have to make exact computations. What happens and what is this operator? And we have to be careful, because in this coordinate, the first coordinate here, this one, we will work with head T1. Here we will work with head T2.
Yes.
But in the end, we've had T, and we have very careful. Okay. And for the next lecture, I will give exact answer.
Okay, thank you very much.
Okay. Unfortunately, Dr. Subject wasn't here for the last half. He said he was having internet problems, so I expect that he will have an opportunity to review the recording, at least of the last part of this lecture that he missed, and he may also have some questions. I'll encourage him to send those questions by email to you, I think.
Okay. Yes. All questions are welcome to my email. If you have some questions, sent to me, then I will answer with using or PDF file. I'll give answers. Okay.
Okay. I have. Sorry.
Page. Any luck in locating courtesy and a little help in locating the recording of my lecture, which was the one of the three past me, the one on the Iso-Differential Calculus. Remember,
all of the recordings are available on YouTube.
We couldn't locate that on the Iso-Differential. The link that you sent me is for my very first lecture, but not for.
But I sent you also some screenshots of the list of the complete list of the lectures that I see when I go to YouTube, and I think all of the lectures are present, but maybe I just don't understand which lecture you mean.
I did not receive those screenshots. I'm sorry. The lecture is an introduction to Iso-Differential Calculus. That's the,
Do you know what the date was?
that look at in January, and that was intended to be an introduction by physicists to the very advanced lecture.
If you could tell me the date, I could easily know for sure, or perhaps the title of your slides, or something that.
Look at the PowerPoint, and from there I should know the date. Yes, I will send it to you. But I'm sorry I did not.
It was of November 3. Not November 3.
No, that was my first lecture. No, the Iso-Differential Calculus was in 2022. No, that first lecture was an introduction to isomathematics in general. That was a very.
Okay.
Or the second, I don't remember. But I'll send you the look at the PowerPoint, and I'll send you the date. But could you please send me a copy of the email? Are now becoming an enormous problem. Google is doing some strange things and with emails. People who have a Gmail have a horrendous problem in getting my emails. They're automatically trashed without notice to me, the sender, and without notice to the recipient. Supposed to be illegal, but apparently it's systematic. And this is the case for millions of other people. So the emails are becoming a major problem. And so I apologize, but that's the way it is.
Okay, I don't have any problems receiving emails from you. They seem.
You know, only for Gmail. Only people who have Gmails is up.
I use Gmail.
But for some reason, others they don't. We just had a major problem in Italy where they have an interview, and 3 or 4 emails from me did not reach them. And so
many people seem to have some trouble with spam, like emails being redirected to the spam folder because for various reasons, I'm not sure why, but if you're missing emails, usually that's the first thing that one should check, is to see whether or not for some reason it became classified as spam. There are a lot of filters on email systems these days because of the problems of spam, and they're like unwanted emails. So the systems try to filter out the unwanted emails, and sometimes they filter out things that you do want. So
that is very true. That is very true what you're saying. The problem maybe due to the improper setting or excessive restriction in the Gmail itself. That is very true what you indicated. Yes. But we are having this problem that many people, I have, not all of them, because you see, this is evidence of your point, Dr. Page. You have an intelligent way of trashing spams, and others that they have general.
If you have a few minutes, we could call this the end of our meeting. But if you have a few minutes, and if Dr. Georgiev would release his shared screen, I could share on the screen with you the YouTube list, and perhaps from that you would be able to see.
Let me call my wife, Manova. She's out, I think, now.
Okay. I'll close my share screen.
Okay.
Yes.
Yes,
Okay.
that's okay.
No.
So now, I think, let me just make sure I'm sharing the correct thing. If I share now, this, you should see now the list of recordings. The last one and the most recent recording was from March 9, was last week.
I have not received this link because mine, what I see, mine is a horizontal band with the command to see the latest. So, but not this one. If you only send me the URL.
Professor Bill, if you select one of these presentation,
For example.
And now, but reproduce that, please. Mm-hmm.
I'm sorry, reproduce?
See, yes, you can reproduce and stop in the way that Professor Santilli can see in the left. Okay, yes, this.
Channel content, that's where I was.
No, only to reproduce the video that you select. Yes, go ahead.
I mean, just to make it play.
Go backward. Oh.
Okay, now you can stop this, and if you move your screen up shortly, you can see the picture of Professor Bill Page, and this says Seminar on Fundamental Problems. If you do click here, not in your picture, but in the seminar legend, then we are going to see the band that with all the.
You mean here?
Yes, yeah, here.
Oh, okay.
Then this is the Professor Santilli used to.
Oh, yes, this is the home screen. Yes.
Mm-hmm.
Home screen. Yeah.
Yeah, the screen that I was showing earlier is the videos screen.
Yes. Mm-hmm.
So
This has a command to extend it to the right, so you can see them all. But we could not, looking one by one, we could not find them.
But see, I'm pointing here at home. You see, I'm pointing at home.
Mm-hmm.
So if I click on videos.
Just a moment, let me see where you are clicking. I'm sorry, can you do it, please? I'm sorry with my eyes. Can you do it again, please? Well, where is home?
Do you see my cursor here with the where?
Okay, perfect. I got
Okay.
it. Now
Next, just to the right is a tab called videos.
that I have seen that one. That we know.
Now, if I click videos.
Yeah, but I couldn't see my lecture. We went through one by one. but we could. But let me try again, and then I'll send you them.
So I see here a lecture on November 3rd as
No, no. It should be January. It should be January, I believe.
more recently.
January 22. No.
Maybe January the 19th.
Can I see it? Can you click on it, please?
This one from January 5th of this year.
Can I see it, please? See the title?
Oh, yes, the title. Oh,
Is
I'm sorry. Let me just a minute. Why did that?
This is important for a number of colleagues who are interested. They want to see them all the lectures, and there is some interest now.
There was also a lecture on October 6th.
2022, that was in this year.
But you would like to see the information about the January 5th?
The title.
The title.
You see, each lecture should have the title to. That's what is
Okay.
to colleagues. They want to know the title of the lectures.
What is it sometimes?
That is why Dr. Page, I suggested that our technician can reorganize these lectures and in a way similar to the similar to other collections of lectures which have title, author, and the link, of course.
Okay, from January 5th, I can, for example, show this. This was on January 5th, we had a discussion of the draft paper, representation of nuclear magnetic moments.
After that, I believe it was after that. But in this list, it should be before, I believe.
The lecture that, so I'm still not clear on what lecture you're.
The title, Introduction to Iso-Differential Calculus.
Well, this one on November 3rd, the presentation was an introduction to Iso-Calculus.
Oh, that's it. So, then can you show
That's,
it?
I already sent that link to you. Yeah.
That turned out to be the one in my very first lecture, an introduction to isomathematics. I could have been mistaken, however.
This says the presentation by Dr. Santilli on the introduction to calculus and its applications.
That's exactly it. So it is there. It was my inability to locate it. I apologize.
Okay, so definitely November 3rd.
November the 3rd. Okay, then that's the lecture. Okay, that some time has passed. My memory.
Okay, and this is the video link right here. I can send that to you right now if you like.
Thank you. There's no, thank you. There is no need to. Now that I know how to locate, I understood where home is. That was the figure, and now I see them all. Yes, and then they
okay, I hope that helps.
They're all in alphabetic, in chronological order. So it's okay.
Yeah, the order is almost chronological. In the first few lectures, I didn't upload them in the same sequence. So they are sorted in the order in which I uploaded as opposed to the actual date. But
very well. Well, appreciate your patience. Indeed, thank you. But now I got the information. Yes.
Okay, that's great.
Thank you again.
All right. So
our seminar are attracting some attention. I can tell you this. People want to go and listen to them at their ease. So the availability of those recordings is fantastic. It's very, very important.
Okay, well, thank you very much for discussions today. And I guess
we lost your voice, Professor Page.
Yes.
Okay, Dr. Georgiev, thank you for your lecture. Thank you for your time. We appreciate it indeed.
Okay, next week at the same time. Yes?
Yes.
Okay.
our plan is
Depending on whether there is a new change
Of the time.
in Florida, we are 1 hour earlier, so it's okay.
okay. Well, I just wanted to mention to Dr. Georgiev that if he feels at some time that he would need more than 1 week to prepare, I don't think there should necessarily any problem in, say, having presentations maybe interspersed, but so long as you wish to continue on this cycle, I think it's at least so far anyway, it seems of interest to me, and I mean, of course,
So,
I think the only comment is I think that our original intention for this series of seminars was to deal with
Hello, we lost you.
more general. So I just,
not voice.
want to make sure that on other subjects.
This is no problem because as I mentioned previous week, there is a ready book on Iso-Differential geometry. And this is no problem week after week because the text is ready. I only have to prepare as slides. Then it's no problem every week. It's
Okay.
circle.
Okay,
So,
thank you.
We'll see you all again next week at 1400. So whatever local time that is for you, I hope it's clear. But if you do have any questions, please send me an email in advance, and I can check that your local time if you have any difficulty determining that.
Okay.
Please, you had a question for me regarding whether there's been any application of the Iso mathematics to computer. And the answer is no, because the application to the computer, the EPR computer, was born in the paper I have submitted to the proceedings of the memorial book. So, Dr. Cruz, any idea when there will be some decision regarding because
Yes, we are now in the step of sending to the evaluation all the received contributions. Yes.
there is a big interest in the computer, and nothing can move until I publish that paper, which is the first paper where the very idea was born. So it will be appreciated if any decision is reached, and if of course within reason, of course within reason.
Okay, well, let's continue our discussions next week.
Okay. See you.
Thank you.
Bye. Bye.
Bye.
Bye. See you.